Okay, so we are doing, we're on our way to doing rigid body kinetics. And I haven't been stressing this, but I really should have been. But we're going to be, like for the first, almost the whole class, we're going to be doing rigid body kinetics in 2D. And there aren't too many things where 2D and 3D are like fundamentally different. But with rigid body kinetics, you have to approach 3D problems sort of fundamentally differently. And so we're not getting into that now. I think we're going to get to that right at the end briefly, just so you see what it's like. But all this, these equations that we're headed for are 2D equations. So these are going to be our rigid body kinetics equations of motion for 2D. And it's going to be F net is equal to mass times the acceleration of the center of mass. And actually, now that I think about it, I think I even said that, I think I even gave the number of equations that you get out of each of these for 2D and 3D. So let me try to correct that stuff. So F net is equal mass times acceleration of the center of mass. And then we have the net moment around the about point is equal to the mass moment of inertia about the about point times the angular acceleration. And this A has to be either fixed or the body's center of mass. Okay, so if the body doesn't have a point that's fixed to the coordinate system, then you have to use the center of mass. Okay. So this one works in 3D. You know, 2D and 3D. This one really only works in 2D. And I'm going to explain why that is. And what you have to do differently if you're going to 3D. So to come up with these equations, and we're going to be able to do problems by the end of today, we had to define three things. The first one was the center of mass. The second one was the mass moment of inertia. And we're done with both of those. And so the last one we have to do is the moment of a force. And we'll just call it a moment. So, okay, the moment of a force. So let's say that this is the body, and this sort of looks like maybe it's a 2D thing, but this definition is totally valid for 3D. And let's say that you have at some location P, you have some force acting on the body. And at some other location, you have your axis of rotation. So this is either going to be, for us, a fixed point, like a joint that connects the body to the coordinate system, or it's going to be the center of mass of the body. And we'll define a vector that goes from that about point to where the force is applied. And that is rho, and you can always calculate rho as P minus A, just from the coordinates of those 2 points. And so based on those definitions, the moment of that force about A is equal to rho cross F. Okay? And in Physics 1, I think when you did this, you probably thought about it more often as like, you found like the perpendicular moment arm, and then you multiplied those two, and then you thought about clockwise and counterclockwise, but the cross product does all that for you. Okay? I always calculate these in like a table form. If you've taken statics from me, you've seen this before. So I always do these in a table. I think it helps you avoid forgetting stuff. And the table looks like this. So like, for example, so you always have these 3 columns: rho, F, and moment. And then each individual force acting on the body has its own rho in this column. So like if, let's say that a body has a force F acting on it, a force R acting on it, and then let's say it has a pure moment acting on it that I'll call M, and I'll talk about that in a second. That's a couple. Okay, so the first thing you do for each rho is for the force that you're dealing with, you have to figure out that rho vector that goes from the about point to where the force is applied. So let's say that that's 0, 2, 1 for this one. And then let's say the force F is 0, 6,500, 0. Now the moment, you know, you can do this in your calculator, just calculate that cross product. You also can do it like this. For the x component of the moment, cross those 2 out, and then it's this times this, minus this times this. Okay, so that's negative 6,500. And then for the y component, cross out the y stuff. And do the same thing with the cross product, but y always has to be a little different, so it's the negative in this case. So it's going to be 0 times 0 minus 1 times 0, then the negative of that, so that's just 0 in this case. And then for z, cross out the z components, 0 times 6,500 minus 2 times 0. So 0. And then for r, let's say that the vector from A to where the force is applied is that. Let's say that the force vector is 0, 0, negative 9,000. So for the x component, you have 0, minus 0. For the y component, you have negative 9,000 minus 0, but then take the negative of that. So positive 9,000. For the z component, cross those out, 0 minus 0. And so you get this. And now when you're given pure moments, these are couples. Those are just moments that you add on and they don't depend on the about point. So we're going to forget about all this stuff and just put in whatever the moment component is. Okay, we're going to use this stuff in 2 dimensions. What does that look like? So for example, you could have so your row vector could be, 5, negative 3. Okay. And then 0 for z. Your force vector could be 400, negative 800, 0. Then your cross product, if you're in 2 dimensions, the moment never has anything except a z component. So look at how this works. If you cross out the x's here, since your rho and your f both have zeros in the z position, you're just going to have 0 minus 0 for x. Cross out the y's, you're going to have 0 minus 0 for y. And then for the z's, you're going to have, what's that, negative 4,000 plus 1,200, so 2,800, negative 2,800. Okay. So the only non-zero value ever is going to be in the z component. So to save, time, whatever, you can write this perfectly equivalently as, so here's your rho, your f, your moment. I'm going to just leave off the z's here. So negative 5, positive 3. $400, negative 800. And then to calculate that moment, it's just this times this minus this times this. And you get what looks like a scalar, negative 2,800. Okay, just remember that that's really a z component of a vector. Okay. So these moments are always vectors even when you're in 2D. It's just that in 2D you only have one non-zero component and it's always Z. Okay? So what about couples? You can always think of these as pure moments with no dependence on the about point. So no matter what you choose as your about point, the moment is the same. Okay? Couples are the only things like that that don't, the about point just doesn't have anything to do with it. So why does that work? Well, what is it, I guess, first of all? So if this is your body, and you have these 2 points, and let's say that you have this as your about point, doesn't matter where it is. So that's your point A. And let's say we have a force F this way, you know. And then at this one, we have an equal and opposite force, negative F. Okay? These are equal and opposite forces. That's why it's called a couple. They always come in pairs like this. Let's call this point P1, the one where we're calling the force F, and let's call this one P2. I guess we'll just think of these as points. Okay? And so then, you know, this is the row vector for one of these two forces, and this is the row vector for the other one. And so what I'm going to do is just, and it's really quick and simple, and I'm going to calculate the sum of the moments produced by this couple, this pair of equal and opposite forces. And what we're going to see is that the dependence on A is going to cancel out of the problem. And what you're left with is a moment that just doesn't care what the about point is. It's the same everywhere. Okay? So, why doesn't the total moment of the couple depend on the location of A? Well, let's first calculate the moment that's produced by F. We're calculating the total moment here. And this is row 1 crossed with F. And then we have to add on the moment produced by the other force. So that's plus row 2 crossed with negative F. And now let's use the definitions of these rows. So row 1 is P1 minus A. And row 2 is P2 minus A. And now the cross product distributes just like multiplication does. So we can write this as P1 cross F minus A cross F plus P2 cross negative F minus A cross negative F. And now you can pull the negatives from the negative F's out to the front, and you get P1 cross F minus A cross F minus P2 cross F. That's pulling out the negative sign, plus A cross F. And the only two terms that have A's in them cancel each other out. And if you want to simplify it, then you could simplify it as P1 minus P2 all crossed with F. Okay? So in this specific case where you have two equal and opposite forces acting at a distance, the moment does not have any dependence on what you choose as the about point. Also, since they're equal and opposite forces, you don't have to think about them in Newton's second law. Notice that, like up here in this example, I just crossed all this stuff out. The reason it doesn't matter for Newton's second law, the reason the forces don't matter is because they're equal and opposite. So when you add those two up, you just get zeros here. Okay. Anybody have any questions about that yet?
Yeah.
Yep.
So we're looking at forces here that are not external, or actually internal forces.
Oh, no, those should be external forces.
Right.
Yeah, think of those as external forces. I mean, something's just grabbing it at those two spots, and yep. The best way to imagine a couple is if you, I mean, a screwdriver isn't bad, but if you can imagine imagine that a screw has, on bikes they sometimes do this. Instead of like a screw slot, they have two holes there, and you turn it with some kind of spanner wrench, you know, that goes into those two holes. And then you turn it. Okay. Well, if you're trying to like loosen this thing, you're going to turn it in a way that applies a downward force on this one, an upward force on this one. That has the effect of producing a couple. You don't have any net force on this thing, you know, because you have one going down and one going up, and they cancel each other. But it does have the effect of turning this counterclockwise. Okay, so that's how to visualize a couple. Okay. So now I'm going to give you some general steps for doing 2D rigid body kinetics problems. Before I do that, I just want to point out, like, why does this only work for 2D? Why doesn't this work for 3D problems? Let me rewrite this. Why do the equations of motion given at the start only work for two-dimensional problems? Okay, so let's think of a case in 2D where a body starts in this orientation. Here's the coordinate system. And then at a later instant, it's in this orientation. And all the rotations are happening about the z-axis. Well, about the z-axis, how would you calculate the mass moment of inertia if this is a slender rod? How would you calculate the mass moment of inertia about z? It would be, 1/12 mass times the length squared here. What would it be here about z? Nothing changed. It's still just going to be 1/12 mass times length squared. Okay? So, I sub a about the z-axis is the same in each drawing. Okay. But let's think about the same thing if we're doing this in 3D. So we're still going from this position to this position. Well, so now we have to deal with all the different axes. In 2D, we only have to deal with rotations about the z-axis. So, okay, the same thing is true as it was before about the z-axis. The mass moment of inertia about z here is 1/12 mL squared. But look at what's happened to the mass moment of inertia about the x-axis. We've gone from, so in this configuration, we'd be talking about a slender rod. So it'd be 1/12 mass times length squared. Now that it's changed into a different orientation, this is just spinning about its negligible axis. That is like a mass moment of inertia of 0. Are you looking on that? Can you picture that rotation? This is like barrel roll about this. And in this configuration, y was just barrel rolling like that in this configuration. But in this configuration, now it's a slender rod, and you have to use that different equation. Okay, so in 2D, the mass moments of inertia are constant in time. And in 3D, the mass moments of inertia vary with time. That's why we need a different approach when we go to 3D. Yep.
So just a quick question. If it were like a rod or like a square beam or something, would on the left z and x and on the right y and z moments of inertia be the same? Assuming it was like
it would be
circular or
yeah, it really depends on how big they are compared to the length. Mostly, as long as it's okay. So if the width of that thing, think of like 1/10 as a good cutoff, for calling it a slender rod. So like if the thickness is 1/10 or less of the length, then that's a good approximation. And the reason it's a good approximation is because It's because of that square in the integral definition. So if you're, so if that thickness is 1/10 of the length, then when you square it, you get 100th. And, you know, and so it's a 1% difference or whatever. So I think that's a good cutoff. Any other questions about this? Okay, so this approach that we're getting into now, we're going to only use for 2D. There's ways around it for 3D, but the problem is that, like, if you look at these equations of motion, you know, well, what's this I sub A? At one point in the problem, it's something. At the next instant in the problem, it's something else. And so you need to just format it in a different way. All right, so here's a set of general steps for 2D problems. General steps for 2D rigid body kinetics problems. The first thing is you have to identify whether there's a fixed point or not for the body. So does the body have a fixed point? If it does, then that's the about point. If it doesn't, then the center of mass is the about point. Okay, I'll call this A. So step 2, now that you've identified the about point, calculate the mass moment of inertia about that. Third, draw a free body diagram for the rigid body. Fourth, determine all forces and moments. So this is where you'd be filling out that table. Okay, fifth, you're only going to do this if there's no fixed point. So you only do this if the about point is the center of mass. Use Newton's second law. So F net is equal to the mass times the acceleration of the center of mass. And that'll give you 2 useful equations. Sixth, you'll do this no matter what. You're always going to use this one, the rotational equation. And that says the sum of all the moments around the about point is equal to the mass moment of inertia around the about point times the angular acceleration. Since this is only the z component, this only gives you one useful equation. And then last, if needed, so I'll put this in parentheses again, you might not have to use steps 5 or 7, but if then the question asks you something else about accelerations of other points or whatever, you can calculate the acceleration using the watermelon equation. And often you'll have to combine this with relative motion. So like the acceleration of p relative to the ground is equal to the acceleration of p relative to some intermediate point plus the acceleration of a relative to the ground. It's pretty abstract right now. We haven't done any problems, but anyone have any questions before I get into an example? Yeah.
So if we have no fixed point, we use the Newton's second law. If we have a fixed point, then are we using like the statics version?
If you have a fixed point, then you can just totally skip that. And I'm going to do an example like that first. So let's just see what it looks like, okay? Okay, so let's say that we have a body that's connected to the wall with a hinge. Let's say the mass of this thing is 10 kilograms. It has a length of 2 meters, and it's released from rest. And we'll call this point P. So what's the acceleration of that point P? So first we have to think about if there's a fixed point or not. Is there in this one? Yes. So I'll call that A. A is fixed. And so we're going to calculate the mass moment of inertia of this body around A. Okay. We can do that with the parallel axis theorem. Well, actually, we derived that last time. But this is going to be 1/12 times the mass times the length squared, plus the parallel axis theorem part is the mass times the distance squared from the center of mass to A. So what's that going to be? The distance from the center of mass to A? 1, yep, half of the. So this term is the parallel axis theorem. And we get 33.3 repeating plus 10, so 43.3 repeating kilogram meter squared. Any questions about that? Now free body diagram. It's a pin joint over here at the left, so that's a fully unknown force vector. I'll call that R. And then, yes,
I might be just doing math wrong because it's early.
Mhm.
Wouldn't that be 40 over 12? Is that 33.3 repeating, or that doesn't?
that doesn't seem,
I get 3 1/3.
3 1/3, okay. Thank you.
So you get 3.3.
Thank you. 3.3 repeating, so this is 13.3 repeating. Yeah. Okay, so we have the reaction force at the left, and then we have the weight force that always acts at the center of mass. So this thing has a mass of 10 times 9.81. This is 98.1. And now we can fill out this table. So there's a column for rho, force, and moment. And we're just going to go through all the forces. So the first one is this force R, this reaction force R. The rho vector is the vector from the about point to where the force is applied. So what is it for this force R? Yep.
0.
0, yes, we like those. The force is Rx, Ry. So what's the cross product of 0 and F? 0. Remember, that's a Z component, even though I'm just writing it as like it's a scalar. And then the next one is the weight force. What's the vector from the about point to where that weight force is applied? 1, 0, yep. The force vector is 0, negative 98.1. Bless you. The cross product then is this times this minus this times this. So we got negative 98.1. Okay.
It's a clockwise one.
Clockwise moment, yep. And so now the benefit of this table is that when you have to use Newton's second law, now you have all your forces right here, and that's easy. And you have all your moments right here, and that's easy. It's all just right in front of you, organized nicely, you know. So that's the end of step 4 in my long list of steps. Step 5 says, if there's no fixed point, then you have to use Newton's second law. This one has a fixed point, so we can just skip Newton's second law. We can get where we're going without it. Okay, so no Newton's second law. Now we'll go to the moment equation. And it says 0 minus 98.1 is equal to 13.3 repeating times alpha. And so alpha is equal to negative 98.1 divided by 13.3 repeating. So about negative 7.36 radians per second squared. Okay?
And this would just be the Z component of the alpha vector?
Yeah, that's right. Yep. Well, now we're almost done. The last thing that we have to do is that we were asked for that acceleration at P. We have the angular acceleration. It's released from rest. So the angular velocity is 0. The r vector goes from the center of the circular motion to the point you care about. What's the center of the circular motion of this bar? Yep.
A.
Right. Yep, the hinge is always the center of the circular motion. So our r is 2, 0, 0. And so the acceleration of P is 0, 0, negative 7.36 crossed with 2, 0, 0 plus this whole part is going to go away because that omega is 0. And we get that the acceleration of P is equal to 0, negative 14.72. Any questions about that? What if we wanted to calculate the reactions at the reaction forces, this force vector R at the hinge? How would we do that?
The bulk weight center of mass.
What?
You make that bulk in the center of mass.
So you could do that. Yep, you could do that right from the start. Or now, so yeah, that's great thinking. You also could do it this way, get to the end, get that angular acceleration. Now calculate the acceleration of the center of mass using the watermelon equation. And then go back and use Newton's second law now that you have the acceleration of the center of mass. Okay, so that's something you'll do quite a bit. You know, what if we wanted to calculate R? You'd use the watermelon equation to find the acceleration of the center of mass. And then use Newton's second law. Okay, that's all for today. I'll give you a couple of problems like this to work on.
We have an example this week.
It's not this week, right? I hope not. I think it's after spring break. I can tell you when it is.